Welcome back, everyone. Today, we're diving deep into one of the most transformative areas of AI research, transformer architectures. You've probably heard the term in passing, but what exactly makes transformers the backbone of modern AI? Let's unpack this, starting with the basics, then moving into the technical intricacies that set them apart from their predecessors. So why transformers? To understand that, we need to look at the limitations of older models. For years, recurrent neural networks, RNNs, and their variants like LSTMs dominated sequence modeling. They processed data sequentially, which made them great for tasks like language translation or text generation. But there was a problem: vanishing gradients. As sequences got longer, RNNs struggled to retain information from earlier steps, leading to poor performance on complex tasks. Then came the transformer. Introduced in 2017 by Google's research team, the transformer architecture revolutionized the field by abandoning the sequential processing model entirely. Instead of relying on recurrence, it uses a mechanism called self-attention to weigh the importance of different words in a sentence, regardless of their position. This allows the model to capture long-range dependencies more efficiently. Let's break down the core components. First, the encoder-decoder structure. The encoder processes the input sequence, converting it into a series of contextualized representations. The decoder then uses these representations to generate the output sequence. But here's where it gets interesting. Each encoder and decoder layer contains two key sublayers: multi-head self-attention and feed-forward networks. The self-attention mechanism works by calculating query, key, and value vectors for each word in the sequence. These vectors determine how each word relates to others. For example, in the sentence, "the cat sat on the mat," the word cat might be more closely related to sat than to mat, and the model learns these relationships through training. But why multi-head? Think of it as the model looking at the data from multiple perspectives. Each head focuses on different aspects of the sequence, such as syntactic structure or semantic meaning. By combining these perspectives, the model gains a richer, more nuanced understanding. Now let's talk about position encoding. Since transformers don't process data sequentially, they need a way to understand the order of words. Positional encodings, essentially sine and cosine functions of different frequencies, are added to the input embeddings. This gives the model a sense of where each word appears in the sequence, allowing it to infer relationships based on proximity. What about training? Transformers use masked self-attention during training to prevent the model from cheating. In tasks like language modeling, the decoder only attends to previous tokens, ensuring it generates text step by step without peeking ahead. This is crucial for maintaining the integrity of the training process. But here's where things get really technical: the scaled dot product attention. The attention score between a query and key is calculated as the dot product of their vectors, divided by the square root of the key's dimension. This scaling prevents the softmax function from saturating, which could otherwise hinder gradient flow during training. And let's not forget the feed-forward networks. After the self-attention layers, each position in the sequence is processed through a fully connected neural network. These networks are identical across all positions, but have separate parameters, allowing the model to learn complex transformations. So why does this matter? Transformers have enabled breakthroughs in natural language processing, from GPT-3's text generation to BERT's question-answering capabilities. They've also expanded into vision, audio, and even scientific domains like protein folding. The key takeaway: by decoupling sequence processing from recurrence, transformers offer scalability and parallelization that traditional models couldn't match. But the journey doesn't end here. Researchers are constantly refining transformers, whether through sparse attention to reduce computational costs or Transformer XL for longer context windows. The future of AI is being shaped by these architectures, and understanding them is essential for anyone looking to stay ahead in the field. If you're curious about the math behind self-attention or want to see how these models are implemented in code, hit the subscribe button and check the description for links to resources. Thanks for watching, stay curious, and we'll see you in the next video.